Welcome to AQA GCSE Chemistry 9 to 1 revision video, the rate and extent of a chemical reaction, topic 6. Calculating the rates of reaction. The rate of a chemical reaction can be found by measuring the quantity of a reactant used or the quantity of a product formed over time. The quantity of a reactant or a product can be measured by a change in mass. For example, when we add marble chips, calcium carbonate, to dilute hydrochloric acid, neutralization reaction occurs where carbon dioxide is released, and therefore the mass goes down. If we measure the mass change over time, we can calculate the rate of reaction in grams per second. Alternatively, we can collect the gas produced by displacement of water in an upside down measuring cylinder. In this case, we would measure the volume of carbon dioxide produced over time and therefore measure the rate of reaction in centimetres cubed per second. Finally, we can use the molar gas volume to actually work out the amount in mole per second. Here's a worked example taken from the specimen paper of the new spec. It asks to use figure 11 to calculate the mean rate of reaction up to the time of the reaction is complete. So in this case, what we're going to do is take, for the reaction to complete, so we need to identify when the reaction is complete, and we can see that because the mass of the flask and its contents no longer decreases. So that's going to be at 270 seconds. And then, as we saw in the previous definition of rate, we're going to take the change in the mass. So it's 152, take away 150.3. So the mass loss, or the difference in mass, or the change in mass, is 152.5, take away 150.3. which is 2.2 grams. And the time taken is from when the reaction stopped, when the line no longer decreased, and that was 270, and it started at 0 seconds. The difference in time taken is 270 seconds. And therefore, the mean rate of reaction is 2.2, the change in mass, divided by 270 seconds, the change in time, which gives us 0.00815. Now the question asks to give the answer to 3 significant figures, and therefore I've given it to 3 significant figures. Remember that if it's 0.00, these are not included in the significant figures. In the second part of this question, it asks us to determine the rate of reaction at 150 seconds. Now, and it asks to give our answer in standard form. So we look at the point 150 seconds, and as we notice, what's happening here is the gradient, which will be the difference in mass divided by a difference of time, is equal to the rate of reaction. And we can see that the gradient is constantly changing. It's steep at the beginning, and then it starts to become less and less steep, and eventually becomes horizontal. So we need to calculate the gradient at this point, because the gradient is the difference in the y-axis divided by the difference in the x-axis, which is the difference in mass divided by the difference in time, and of course the difference in mass divided by the difference of time is the rate. So we need to work out the gradient at this point, and the way we do that is drawing a tangent to that line. Now we want to draw this line as long as possible so we get a more accurate value of the gradient. And what we want to do is, when we draw a gradient, we want the line to approximate the gradient at that point. Once we've done that, just like before, we work out the gradient of this line, so we take the difference in the y-axis, which is going to be 151.9, take away the difference here, so it's 150, so 0.9, and then where it intersects the x-axis, difference in the x-axis, and we get mass loss is 1.9 divided by, coincidentally, 270 again, and we have a gradient of 0.007. But it says give your answer in standard form. So that is 7 times 10 to the power of -3. Collision theory and activation energy. Chemical reactions can only occur when reactants collide with each other, and they must collide with sufficient energy. The minimum amount of energy that particles must have to react is called the activation energy, and this was also discussed in the previous video. In the enthalpy profile diagram, we can identify the activation energy because it's the energy required to break the bonds of the reactants, and this is a heat change where heat is transferred into chemical energy, and therefore the N go in, enthalpy, heat, change is positive as energy is transferred from the surroundings in the form of heat to the chemical energy of the reactants as the bond breaking process. Factors which affect the rates of a chemical reaction. Concentration. An increase in concentration increases the frequency of collisions and therefore the percentage of successful collisions. Pressure. Increase of pressure increases the frequency of collisions and therefore increases the percentage of successful collisions. Surface area. The increase of surface area increases the frequency of collisions and therefore more successful collisions. And temperature. Now temperature increases the number of collisions but also increases the proportion of molecules that have the required activation energy. And the presence of a catalyst. And the way the catalyst works is to provide an alternative path lowering the activation energy. So as you can see, the activation energy with a catalyst is lower than without. Effective concentration on the rate of reaction. Increasing the concentration of reactants in solution increases the frequency of collisions and so increases the rate of reaction. At low concentration, we have a small amount of reactants compared to solvent, water. As a result, there is a lower chance of collision. At higher concentration, i.e. a greater amount of reactants per solvent, there is a higher chance of collision and so increase of rate of reaction. The effective pressure on the rate of reaction. Increasing the pressure means there is more reactants per unit volume, so there is an increase in frequency of collisions and so increase the rate of reaction. At low pressure, we have a small number of reactants. But if I increase the reactant of the blue, I get a higher pressure of blue and therefore a higher chance of collision. The effective surface area on the rate of reaction. In solid collisions, only occurs on the surface. So in solids, collisions only occur on the surface. This means that these inner reactants cannot actually collide with the other reactant until the outermost reactants have actually reacted. Now in a large solid, that will mean that only a tiny proportion of the reactants on the surface are able to react. Increasing the surface area of a solid increases the frequency of collision, so increases the rate of reaction. So how is this achieved? And this is achieved by reducing the particle size. So making the pieces smaller means that in this case all of the particles are on the surface and therefore all can collide at the beginning of the reaction. You also need to be able to explain the shapes of graphs. So as we can see, we have a graph showing the total mass or volume of a product over the time of the reaction. Now remember, the difference in the y-axis is the difference in the x-axis. It's called the gradient. But in this case, a change in mass or volume over time is also the rate of reaction. So you can see from these two lines that the steeper line, therefore the one with the faster rate of reaction, happens with something with a larger surface area, e.g. a powder, as opposed to something with a smaller surface area, lumps. Note also that they both finish in the same place. That's because we have the same amount of reactant, the only variable that we've changed is the surface area. Because the rate of reaction of the powder is faster, the reaction completes more quickly, as opposed to the lumps, which take longer to finish, indicated by the line becoming horizontal, or the gradient becoming zero and therefore the rate becoming zero. The effect of temperature on the rate of reaction. Increasing the temperature will increase the frequency of collisions and make the collisions more energetic and so increase the rate of reaction. That is, that more of the reactants will have the required activation energy to react. At low temperature, many collisions result in unsuccessful collisions, whereas at high temperature, there are more successful collisions. If we have a look at this graph, again, we have the volume of gas produced or the mass produced of a product over time. And again, the gradient will be equivalent to the rate of reaction. And what we can see is that the steepest line, i.e. the one that has the faster rate of reaction, is at higher temperature. This is because the particles have more collisions and also more effective collisions because more of the particles have the required activation energy. And we can see that the reaction finishes much more quickly than the equivalent temperature at lower temperature, which finishes here. Again, they both end at the same point because they both start with the same amount of reactants. Catalysts. Catalysts change the rate of a chemical reaction but are not used up during the reaction and therefore they're not called reactants. Catalysts increase the rate of reaction by providing an alternative pathway for the reaction, and as we can see from this enthalpy profile diagram, we can see the energy of the reactants. We can also see the amount of energy that we need to put in for the reaction to occur, called activation energy. Firstly, we can see the activation energy required in the uncatalyzed reaction, which is larger than the alternative path provided by the catalyst with a lower activation energy. Notice that the change in energy overall for the chemical reaction is the same because the difference between the reactants and the products is the same. Different reactions need different catalysts. Enzymes are examples of biological catalysts. Here we have a worked example taken from the specimen paper of the new spec. Explain in terms of particles how and why the rate of... Here we have another worked example from the specimen paper of the new spec. Explain in terms of particles how and why the rate of reaction changes during the reaction of calcium carbonate with hydrochloric acid. And to help, I've added in the graph that was given in the question. And what we can see is initially the difference in the mass over time, that is the gradient, is steep at the beginning and then becomes shallower and shallower and then eventually becomes horizontal. That is, the rate at the beginning is high and then decreases and then eventually becomes zero. The reaction stops. And it's asking you to explain in terms of the particles how and why this occurs. So the first thing to say is that at the beginning we have lots of acid and lots of calcium carbonate. But as the reaction proceeds, both the calcium carbonate and the acid is used up. And as a consequence, the concentration of the acid decreases, and therefore there are less frequent or fewer collisions per second, and therefore the rate decreases or slows down until it eventually stops. Required Practical 5, investigate how changes in concentration affects the rates of reaction. You can determine or measure the rate of reaction by measuring the volume of a gas produced over time. For example, you can use marble chips, which is calcium carbonate, and add hydrochloric acid, which of course will make calcium chloride, water and carbon dioxide gas. And if we do this in a stoppered conical flask, the carbon dioxide produced can go down the delivery tube and go into an upturned measuring cylinder full of water and displace it, which means that we can measure the volume of gas produced over time. Now, if we vary the concentration of the hydrochloric acid, we can see the effect of hydrochloric acid over the rate of reaction. And in this graph, we can see the effect of changing the concentration from 0.5 to 1 to 2. And we can see that by increasing the concentration, we increase the rate of reaction. That is, the change in the volume of CO2 produced over time. We can also see that at higher concentration, the reaction finishes more quickly than at lower concentration. Another experiment you can do is by adding acid to sodium thiosulfate solution. And in this reaction, sulfur is produced, which is a yellow solid. By drawing across on a piece of paper and putting the conical flask with the solution above, and as the reaction proceeds, an opaque solution of sulfur is produced, meaning that you can no longer see the cross. And we can measure the time taken for the cross to disappear. And as we can see in this graph, that again, if we conduct the experiment at high concentration, we have a faster rate of reaction than if it's at lower concentration. Reversible reactions and dynamic equilibrium. In some chemical reactions, the products of the reaction can rate to produce the original reactions. Such reactions are called reversible because they can produce reactants to products and the products can go back to reactants. And these reactions are represented using these double arrows to show that the reaction can be reversed. An example of which will be copper sulfate pentahydrate. That's copper sulfate with 5 moles of water in the water of crystallization. Now, if we heat the hydrated copper sulfate salt, we can actually remove the water and we can produce the anhydrous copper sulfate salt, which is actually a white powder because it was the water that made the copper sulfate appear blue. Now, this can obviously be reversed by adding water back to the anhydrous copper sulfate to make the copper sulfate pentahydrate. However, at any point it will be either one product or the other. Equilibrium. When a reversible reaction occurs in the apparatus which prevents the escape of reactants and products, it is said to be a closed system. That is, nothing can get in or out. And if the reaction forward and back happens at the same time, it can reach a point called equilibrium. And that is because the rate forward and the rate back are the same. Now, many students have a misconception here where they think that equilibrium means that the concentration of the reactants and products are equal. This is not the case. It's the rate that the forward reaction and the backward reaction occur are the same. So that's the equal bit in the equilibrium. And if we look at this graph at the beginning of the reaction, we can see the rate of the forward reaction producing NO2 is much higher, and then the rate backward of the N2O4 producing 2 moles of NO2 decreases until the rates are the same. That is, that the rate forward and back do not change. But we can see that the concentrations of each are not the same. We have a higher concentration of NO2 than we have of N2O4. The effect of changing conditions on equilibrium. The relative amounts of reactants and products at equilibrium depend on the conditions of a reaction. If a system is in equilibrium and a change is made to any of the conditions, the system opposes the change. It responds to counteract the change. The effects of changing equilibrium can be predicted using the Chatillon's principle. Two analogies for this are that if one person is digging a hole in the ground and moving the earth out, and the second person replaces the earth back into the hole at the same rate, the size of the hole or the pile of dirt will stay the same. Or another analogy are that if we have a look at this system where we have water being added to one and the two containers are connected, as we continue to add water into the left-hand container, this will move more water down, so the level will be the same because the pressure on both of air is the same. So after changing the volume in one, the volume will decrease by the same rate as the second container increases, and we'll have the same volume in each container. If the concentration of one of the reactants or products is changed, the system is no longer at equilibrium, and the concentration of all the substances will change until the equilibrium is reached again. If the concentration of a reactant is increased, more products will be formed until the equilibrium has been reached again. For example, if we increase the concentration of a reactant, represented by the red balls, the equilibrium position will shift to reduce the reactant concentration, that is, favouring more products. So therefore, the reaction forming the products will be favoured and the rate will increase. In the example below, the new equilibrium mixture will contain a higher concentration of C and D. If the concentration of a product is decreased, more reactants will react until the equilibrium is reached again. So in this case, if a product concentration is increased, represented by an increase in the number of blue balls, the equilibrium will oppose the change, that is, decrease the concentration of the blue balls by forming more reactants, represented by the red. The effect of temperature changes on equilibrium. If the temperature of a system at equilibrium is increased, the relative amount of products at equilibrium increases for an endothermic reaction. That is, as you've increased the heat, the equilibrium will oppose the change by decreasing the heat. And the way that reaction can decrease the heat is to favour the endothermic, N to take in, thermic heat reaction. The relative amount of products at equilibrium decreases for an exothermic reaction, that is where the forward reaction is exo. The effect of temperature changes on equilibrium. If the temperature of a system is decreased, the relative amounts of products at equilibrium decreases for an endothermic reaction because it opposes the change by increasing the by trying to increase the temperature by favouring the exothermic process. So if the forward reaction is endo, the yield will decrease. However, if the forward reaction is exothermic, then the decreased temperature, will favour the forward reaction. If we have a look at a worked example, in industry, ethanol is produced by the reaction of ethene and steam at 300 degrees and 60 atmospheres of pressure. We have 1 mole of ethene reacting with 1 mole of steam to make 1 mole of ethanol. And the question tells us the forward reaction is exothermic. It asks you to use Le Chatelier's principle to predict the effect of increasing temperature on the amount of ethanol produced at equilibrium. Now, the best way to do this is to chunk the answer. So we identify if the forward reaction is exo, and we place the word exo above, and if the forward reaction is exo, then the backward reaction must be endo. And then we think, okay, well, if we increase the temperature, Le Chatelier says the equilibrium will oppose the change. So the opposite of increasing the temperature is to decrease the temperature. And the only way it can do that is by favouring the exo or the endothermic process. Now remember, exo means to give out heat. So that will actually make the temperature even hotter. So what does it do? It favours the endothermic process. The increased heat will be taken in by creating more of the reactants, and therefore the yield of ethanol will actually decrease as we increase the temperature. So the amount will decrease because the equilibrium will oppose the change. It will move to the left. Now, you might think to get the best yield, we would cool the temperature right down to minus 200 degrees. But of course, this will also affect the rate of reaction. So in practice, we need to have a compromise between the rate and the yield. The effect of pressure changes on equilibrium. For gaseous reactions at equilibrium, an increase in pressure causes the equilibrium position to shift towards the side with the smaller number of molecules, as shown in the symbol equation for that reaction. So if we increase the pressure, the equilibrium will oppose the change to decrease the pressure, and that will favour the side with the fewest number of moles of gas. For a decrease in pressure will cause the equilibrium position to shift towards the side with the larger number of moles of gas. For example, explain how increasing the pressure of reactants will affect the amount of ethanol produced at equilibrium. Again, the best thing to do is chunk the answer to make this simpler. And what we do is we draw a square box on either side and we put in a dot to represent the number of moles of gas on either side of the equation. So there's my box, and I've represented the two dots to represent the 2 moles, 1 mole of gas and another mole of gas. And I also, on the right hand side, draw a box and I represent a dot to represent the moles of gas. Remember, only gases can exert a pressure. So if you've got solids or liquids on either side, do not include them in this step. And then we count the number of moles of gas on each side in the boxes, and the one with the highest amount of gas was the higher pressure, and therefore this is the lower pressure. So remember, we're going to use Le Chatelier's principle to say if we increase the pressure, the equilibrium will oppose the change by decreasing the pressure, and the side with the lowest pressure is the right hand side, and that is the product that we're trying to make. So by increasing the pressure, the equilibrium will oppose the change and favour the forward reaction, the side with the least moles of gas, and therefore the amount of ethanol will increase because the system moves to the side with the fewer moles of gas.